All right, I'm pretty sure we discussed this last class period, that some of the fractions that are in the rhyme papyrus have multiples of 3 in the denominator. So I'm going to pick on one real quickly. For instance, let's say 2 over 27. That's a multiple of 3, right? Where 27 is, the multiple of 3 that it is 3 times 9. So if I were looking at this particular formula, 2 over 3k, in that case, the k would be a 9, right? So we know that we can decompose that into the unit fractions. 1 over 2 times 9, which would be 1/18. Right here we see, oh, look at that. They had that, 1 over 18, the Egyptians, 3,000, maybe 1700 BC, whenever that was. Okay, and then the other one can be 1 over, and again my k is 9, so 6 times 9 is 54. And here we see that they had that also. So it's interesting because at least for our purposes, it seems like every time they did a multiple of 3 in the denominator, so often we'll see, every third one basically, that it seems like they've used this 2 over 3k formula. So people find that really interesting that that's in there. However, they don't seem to have necessarily a set formula for other stuff. So this one, you'll find it in your book. In fact, I think one of the homeworks is to prove that. So 2 over n, any 2 over n, we don't have a restriction on what that n is, can be written 1 over n plus 1 over 2n plus 1 over 3n plus 1 over 6n. And one of your homework questions says to prove that. And you'll prove that like a trig identity, where you work on the more complicated side, you don't cross the equal sign, and you work to combine these fractions. Normally you would get an LCD and cram them all together, and then things will reduce out and you'll end up with 2 over n. So therefore you know they're equivalent, so you're golden over here. But whenever I look at that, that requires me to break this thing down into 4 different fractions. And clearly, for 2 over 27, they weren't doing that, right? It's only 2 fractions. Now, it's possible they might have had something like that in some of the places, but we're not necessarily seeing that they knew that and used that, because clearly they didn't on all of them. Like on the 2 over 25, for instance. 2 over 25, I could use this and write, okay, 1 over 25 plus 1 over 50 plus 1 over 75 plus, now I'm in trouble, 1 over 150. Okay, so, but they didn't do that. So they clearly had it for 1 over 1/15 and 1 over 75. Sometimes it looks like maybe they pulled out the largest unit fraction, which we're going to talk about that as one of our techniques today. Some of them, except for the ones where 5s, the denominators are divisible by 5s, a lot of them are even numbers. So you've got a half at the beginning, a fourth at the beginning, a sixth, an eighth, a tenth. So you'll see all these, and then suddenly I hit a multiple of 5, and that one's got, you know, just 2 odd numbers in the denominators. So that's interesting. But a lot of even numbers there starting out. So maybe there's something about pulling some kind of even number. Dr. Dorsett, who's a retired faculty member in our department, not too many years ago, found a cool little pattern inside of the rhyme papyrus table. So it's interesting to me because these really ancient texts and way of doing things still spark interest in modern day mathematicians, and they're like, hey, what do I do with that? What can I find in that? Can I explore it a little bit? Can I see what's going on? So you know, he wrote a thing, he saw a pattern, and he used it. So it's really pretty cool, I think. Oh, here's an example. Sorry. Looking at this, the n, the 2n, the 3n, the 6n on the bottom. Look at 2 over 101. 1 over 101, 1 over 202, 1 over 303, 1 over 606. So it looks like that, right? So who knows exactly which patterns they saw and which ones they didn't, but we can find some of the stuff, and it's interesting that modern day mathematicians are still playing with it and still trying to find stuff. Sometimes our unit fraction decompositions will match. what they had in the rhyme papyrus, and sometimes they don't. And so that's okay. We'll just work it out. So one of the methods we're going to look at today is called the splitting identity. Okay, the splitting identity is actually another formula. So again, this notation that we're using these days, this is very modern notation, right? And so clearly they didn't use that with the Egyptians. This is algebraic notation, but it makes sense to us. So what I tell my undergrads is, you guys are probably going to like this one because it's very mathy, it's very modern math. And so somewhere in your notes, maybe mark down the splitting identity. If you use it enough times as you do your homework, it'll become normal to you. You'll remember it. So what the splitting identity says is if you take 1 over n, any 1 over n, you can split that into 1 over n plus 1 plus 1 over n times n plus 1. Okay? So what I'd like for you to do is everybody maybe pause the video for just a second and see if you can prove it. Can you prove this? We're all in graduate math classes. Hopefully we can prove this. It's a fairly simple one. Pause the video. If you don't want to pause it, then you can work it along with me. But if you want to take a shot at it, take a shot. Okay. So in my world, I'm going to say, oh, these two on the right-hand side, this is the more complicated version. Clearly 1 over n is very simple. So I'm going to try to combine these two fractions and make them look like the left-hand side. So the denominators are the same, except for this one needs an n, right? If I multiply the bottom of the fraction by n, I multiply the top of the fraction by the n. So now I have 1 over n on the left-hand side is equal to n over n times n plus 1 plus 1 over n times n plus 1. Okay. So probably a lot of you can see it at this point, but I'm going to go ahead and work that out. I'm going to cram them together. That's an n plus 1 over n times n plus 1, right? And if you didn't see it before, you certainly probably see it now. The top there is the same as this portion of the bottom. Those will reduce. And now I have 1 over n, right? Which is what I was after. So the right-hand side really is equivalent to something that looks like the left-hand side. So therefore, I've proven that these are equivalent. So we can use it. Yay. Now in our modern mathematics, we know once we've proven something in a generic sense like this, it means I can use it on any 1 over n, right? But the problem is that it works for 1 over n. And if I wanted to decompose a unit fraction into 2 more unit fractions, okay, but that's not necessarily going to help me, right? So it doesn't necessarily make a ton of sense for me to do that. So what I'd like to do is I'd like to use the splitting identity for 2 over 7. And I'm picking 2 over 7 first of all to do this one first because we know we have that in the rhyme papyrus. It's a 2 guy, 2 over n. So we'll see what that looks like in a second. The trick to this, and you don't have to do it like this every time, but I'm going to do it so that I can show you what's going on. The trick to this is to make this 2 over 7 look like it's a 1 over n. So that's going to be, to me, I'll pull the 2 out, and it's 2 times 1/7. Okay. So if I ignore the 2 for just a second, this looks like a 1 over n, which is the left-hand side of my splitting identity. So on the right-hand side, I'm going to have 1 over n plus 1, which is just an 8, plus 1 over the n, which was a 7, times the n plus 1, which is an 8. Okay. So I'm just using the splitting identity. I'm just rewriting it with the n equals 7 here. I'm just substituting n. But the difference is what? Yeah, what my finger's covering up, right? This wasn't really 1 over 7. It was really 2 times 1 over 7. So we have to remember that we have that 2 guy sitting out there. But this is pretty easy because whatever I do to the left-hand side of an equation, I have to do to the right-hand side of an equation. So basically, everything over here needs to be multiplied by a 2. Okay? That keeps my equation nice and balanced, and I'm okay, right? So this turns back into 2/7, which is great. That's what we wanted on the left-hand side. But over here, look, sometimes it works out nice and pretty like this because these are in the 2/n table in particular. They're odd numbers. So once I add 1 to it, that makes it even. So I've got this nice, pretty even piece in the denominator of both of those other fractions. And if it's a 2 guy, well, we know 2 will reduce out, right? So that makes my life lovely. But in a second, we're going to see one where we go, well, what if it was a 5 sitting there? Okay, if it's a 5 sitting there, that doesn't help me with the 8, right? So maybe that doesn't help me at all to do it that way. Who knows? But here it's nice because the 2 reduces with the 8. I get 1/4. And here the 2 reduces with this 8, and I get 1/28. Okay, and interestingly enough, I've got 2/7 is equal to 1/4 plus 1/28, and when I pulled this up, look, there it is. It's actually exactly the same as what they have in the rhyme papyrus, which is kind of cool. Awesome. Okay, so that makes my life nice and pretty because it reduced, right? But they don't always reduce, so we can't always just bet on that, so dang it. All right, so here's what we're going to do. We're going to do a different problem. I'm going to give you a second to think about it. By the way, in your directions on a test or something like that, it would say something like decompose. We're going to do 5/17 into the sum of unit fractions. A sum of unit fractions, something like that. Okay. But you'll know what we're after because it's going to talk about decomposing. It's going to talk about unit fractions. And then in this one, I'm going to say using the splitting identity. And I don't care that you memorize that. I think you'll remember it once you write it down for a few homework questions. But just for our purposes, so that you have it in your notes somewhere, remember this is the splitting identity. Put it somewhere. Make yourself a little index card or something with formulas. I don't know. Whatever study habits you have that help you out, do that. Okay. So we're going to use this. Well, I'm working with 5/17, so I don't want 5/17 right now. I'm just going to do 1/17. So if it were 1/17, then I would have 1/17 is equal to 1/18, because my n is 17. 17 plus 1 is 18, sorry. Plus 1 over the n is 17, and n plus 1 is 18. So that's what it would look like, right? All right. So that would be all lovely if I had started with 1/17, but I didn't. I started with 5/17. So now you have to step back for just a second and go, okay, what are we going to do? Well, we're going to multiply the left-hand side by 5. You can write it 5/1 if you want to. And when I do that, I multiply the right-hand side by 5/1. And that's all fine and dandy, except that this doesn't make it look any prettier. 5/17 is equal to 5/18 plus 5 over, I'm going to leave that 17 times 18 for now. If we need to multiply it in a second, we will. Okay, so it doesn't really look that much prettier at the moment. So people are like, well, why would we bother doing it with something like that? And the problem is that 17 is, first of all, a prime, second of all, odd, and third of all, I've got a 5 on top, and that is not going to reduce, right? So those are my issues here. And 17 is kind of a large prime. Well, for what we're doing, not overall, but it's for what we're doing, it's kind of big. So, oh my goodness, what to do? Well, for purposes of the test, you only have to use whatever method I asked you to do once. So we've already used splitting identity. So I'm good as far as wherever you want to go from now, whichever rabbit hole you want to go down, I will follow you. But at this point, we might think for just a second about well-chosen numerators. So like this isn't getting any better. If you wanted to, you could split this, for instance, into 1/18 and 4/18, but that's not very pretty. Maybe I could pull 2/18 out of it and try to use the rhyme papyrus and then figure out what I'm going to do with 3/18. But if I really look at it, other than using the rhyme papyrus, there's a problem with that because it's even, right? So the real thing would be, can you think of splitting it nicely? So let's talk about what I just said. 2/18. What do we know about 2/18? Oh, that's going to reduce down to a unit fraction, right? Plus 3/18. Well, that's also going to reduce down to a unit fraction. So if I can kind of play a little bit with the numerators and the denominators to see what could I make the numerator be so that it still adds up to give me the 5 there, right? But these numbers are nicely divisible with the bottom. They have something in common that I can factor out. If I can do that, then that'll actually pay off for me nicely, because over here, the 18 is still in the denominator, right? So I can still do a similar reduction. I just have to be a little more careful about what that denominator is going to be there. Oh, sorry, that should have been a 2. So I'm actually going to do the same exact splitting on the right-hand side. I'm going to make it a 2 and a 3, but with the bigger denominator here. Okay, so let's see what happens here. 5/17 equals, well, this is 1/9. Yay, we like that. This is 1/6. Yay, we like that. The 2 will go into the 18 9 times, and if my arithmetic is correct, that should be 1/153. So check my arithmetic on that, but I'm pretty sure I'm right. Okay. And then the 3 will go into the 18 here 6 times, so that should be 1/102. And again, dig out your calculator, or whatever you need to do, check my arithmetic, and see if it works. But I'm pretty sure that one's okay. All right. Now the problem with this is that this was a 5/17, so is it on my rhyme papyrus? No, it's not in my 2/n table. So I can't double check and try to see what the Egyptians might have done with that one. However, you can play with it a little bit. If you want to make sure this really is congruent or equivalent, you can get a common denominator amongst these. It would be 17 times 18. Get a common denominator amongst all these, add them back together. You better get something that's equivalent to 5/17, right? So check it, make sure it works for you. This is probably not, well, we know it's not using that rule up above that we had with the 1/n, 2/n, or 1/2n, because it's not a 2/n guy. So it's just an interesting split up decomposition of 5/17. So there we go. Yay. There are other things you could do up here if you didn't see to split it into 2 and 3, but I would hope that you could kind of use some of your number sense, a little bit of your mental arithmetic kind of stuff, and see where you want to go with that. So hopefully that makes your life easier, not harder. One more of these. Let's decompose using the splitting identity. And this one will be in my 2/n table, so we'll check it in a minute. 2/53. And what I'd like for you to do is just do it. Go have fun with it. I'd like you to use the splitting identity, so you know what that one is now. I'm going to work it out, and I'm not going to take as much time to explain it. So if you need a chance, play with it. You can pause and come back and see what we do here. Okay, so I've just plugged it straight into the splitting identity, added 1 to the bottom, see where I'm going here. 2 goes into 54/27 times. I think that 2/53 is equal to 1/27 plus, sorry, I didn't multiply that just now. I did it in advance. 1/1431. So check my arithmetic, 53 times 27. Okay, that's my answer. Like I said, pause it if you need a little bit of time to play with it, but that's what I think it is. Now we're going to go look. So this is the splitting identity. We know this is modern math. We know this is not necessarily what Egyptians did, but the question is, did they have that pattern? Did they see it? And when we go to 2 over 53, we see, well, if they had it, they didn't have it for this guy, right? Because you would think 53 is one of those weirdos that maybe they would have used a pattern like this for, but they don't have it. They've got 1 over 30 plus 1 over 318 plus 1 over 795. So clearly they did not use that. Now, if you want to confirm that those are equivalent, you would just get common denominators on all of them and make sure that they all reduce back down to 2/53. Okay, so that's what I'm looking at there. I think that that's pretty straightforward. You've got some homework that I'm going to assign that uses the splitting identity. So if you have any questions, go back and look at them. I do have some problems that you can practice with that are not too terribly difficult. And you can use these for both the splitting identity and the method we're about to use both. So if you want to play with them, some not too terribly big problems are 5 over 6 and 6 over 7. Those could be used to figure out, hey, do I know what I'm doing or not? And if you're curious, you can talk to a friend or see me or whatever if you need help making sure that your stuff is right. I thought I had another example. At one point I used 2/19, I think we did that one for the splitting identity already. 5/17. We'll work a couple of other problems with the Fibonacci, and anytime we work any example, like we've already worked 2/7 and 5/17, if you want to work those using the other method, I'm not always going to do that. Sometimes I will, but not always. Excuse me. But if you want to work that using the other method and see, does it come out the same? Do I get something that's equivalent? Does it look right? Those kinds of things, then feel free. All right, so my second method. The second method for the evening is called Fibonacci's method. And Fibonacci's method is actually maybe a bit of a misnomer. If you don't know who Fibonacci is, go look him up. We'll talk about him probably around spring break. He had a lovely sequence that looks like this. That very quickly starts getting big, and within 3 or 4 more terms of this sequence, you'll be at 144, so it gets large very quickly. So, but the trick to it is that it's a recursive formula. So in order to get the 2, for instance, you would add the 2 terms in front of it. So 1 plus 1 gives me 2. To get the 3, I would add the 1 and the 2. 1 plus 2 gives me 3. To get the 5, I would add the 2 plus the 3. To get the 8, I would add the 3 plus the 5. 13, you add the 5 and the 8. Okay, so you see that it's recursive, meaning that it always refers back to the terms, in this case, 2 terms before in order to get the next term in the sequence. Sometimes with recursive stuff, you only look at 1 term, but this one is actually 2. And there's a huge story about that. We'll talk about it when we get to Fibonacci. All right, so kind of one of the beliefs is that because there's a repetitive feel, this looking back thing and adding the 2 and adding the 2, that what we're about to do is, that might be one of the reasons why Fibonacci got a little bit of a namesake for it. There's not a lot of work that he did with this, but yeah. So here's the idea behind Fibonacci. Always pull out the largest unit fraction possible. Always pull out the largest unit fraction possible. And sometimes that works out really nicely, okay? So if we're always pulling out the largest unit fraction possible, for instance, I don't know if I used this in this class or not the other day, but if I had 5/8, 5/8 is actually a really, if you're doing it and you're paying attention and you really pay attention to what you're doing, it's pretty easy to decompose this one, right? I would do 1/8 plus 4/8. Okay, and the reason I picked 4/8 is because 4/8 will reduce down to 1/2, and 1/2 is the largest unit fraction, right? So 1/2. Okay, I can take a pie and cut it in half, and that's a terrible pie, but you get the point. So the shaded part would be 1/2, the not shaded part would be 1/2. So that's the largest one. The next largest is 1/3, right? 1/3, 1/3, 1/3. And if I want, I can shade one of those. Okay, so then that's the next largest piece of the pie, and so on and so forth. So the largest possible unit fraction is 1/2. So when I did this, I said, hey, look, 5/8 is just barely bigger than 4/8, but I know that 4/8 is, I don't want to do it like that. Sorry. I know that 4/8 is actually 1/2. So when I pull out that 1/2, and by pull out, in this case, I mean what? Like mathematically, it means subtract, right? And in this case, whenever I subtract out the 1/2, I have a 1/8, and that guy is a unit fraction, so I'm done. Oh, that's lovely. 5/8 is the same as 1/2 plus 1/8. Ta-da, done, easy. That's why I meant by easy. So if you happen to see, hey, I can pull out a 1/2, that's a really big unit fraction, and it only leaves me with one little unit fraction left over, that is lovely, and kudos to you, and that makes our life easier. If not, if I pull out the largest unit fraction and my remainder is not a unit fraction, then using Fibonacci's method, I would do it again. Okay. Keep on working with the remainder, pulling out the largest unit fraction you possibly can until the remainder is a unit fraction, and then you'll write it as a sum of all those unit fractions. All right, no worries. So here's the problem. That one right there was super easy, right? I did that in my head. Yay. Because I knew that 4/8 comes out of 5/8 and that 4/8 is 1/2, because those were, in my head, pretty easy fractions to work with, right? But that's not always the case, unfortunately. So here's one that's not quite so nice. Decompose 2/19 into the sum of unit fractions. In this case, we're going to use Fibonacci's method, which means pull out the largest unit fraction you possibly can and continue doing so until you get down to a unit fraction. All right. So the problem here, at least in Webster brain, is that 2/19 is not a nice fraction. 19 is not only odd, but it's also prime. It's kind of a large prime for me to be dealing with. I've only got 2 pieces here. Earlier I knew 5/8 was bigger than 1/2, but this is only 2 little bitty, 19 pieces. If I take a pie and I slice that sucker into 19 pieces, those little pieces are going to be small, right? And I only have 2 of them. So I don't know what the biggest unit fraction is that'll subtract out of that. Maybe you do, okay? What I do know is I can't split it into 1/19 and 1/19 because that would be repeating the same unit fractions, and we know the Egyptians don't want me to do that. So I can't do that. So it would be helpful if I had a little trick. I know 1/2 won't come out of it. I know 1/3 won't come out of it. 1/4, if this was a 20, 1/4 would be 5 pieces, right? So I know 1/4 won't come out of it, but I don't want to go through every single little unit fraction like that. So what I'm going to do is I'm going to do some work off here on the side. I'm actually going to call it an aside. This is my scratch paper, right? So maybe some people call this scratch. This is not really part of my problem. This is just for my benefit. There's a technique for figuring out the largest unit fraction. Once you get it, you can kind of play with it a little bit and do things that maybe help you remember it. And maybe you don't have to do this every time, but I'll show you what it looks like. So 2/19, it's just hard to wrap my brain around. Instead, what I'd like to do is deal with whole numbers instead of little fractions, or as close as I can get. So what I'm going to do is I'm going to flip 19 halves. Okay. And I'm going to say there's a whole number that's less than 19 halves, and there's a whole number that's larger than 19 halves. So I'm going to do a sandwich type thing. So it's not the sandwich theorem like you would see in calculus, but it is a sandwich type thing. So in my head, I'm going to say, well, if this was 18 halves, that would be 9. So 9 is the whole number that's slightly smaller than this. And if it was 20 halves, this would be 10. So 19 halves is actually 9 and a half. And so it's halfway in between those two whole numbers. Okay, makes sense, right? Pretty easy. Some people might want to convert this. You might say this is 9 1/2, or you might say this is 9.5. You know, if you're better with decimals, that's fine. Okay, I'm just going to leave it as a fraction. So what happens is, I know that if I had flipped this and made it 19 over 2, these are the whole numbers it would be between. I don't want that though. I want the fraction part. So maybe you can see where I'm headed for. If I flip it back, that would be 2/19. But now I have this little inequality sentence going on here, right? So I need to flip everything. So this would become 1/9. This would become 1/10. And FYI, when I say everything, I mean everything, right? Because I'm not dealing with whole numbers anymore. Now I'm dealing with fractions. And we know the bigger the denominator, the smaller the piece when I've got the same unit here, right? So 1/10 is actually smaller than 1/9. So I need to flip these signs as well. So the smallest thing here is the 1/10. Okay, so wrap your brain around that for a second. All right. So take a second to process that. I flipped it, I stuck it between two whole numbers, and then I flipped it back over, and that gets me to between two fractions. Okay, now I actually want to subtract from the 2/19, right? Which means I need the fraction that is smaller, because the fraction that's larger, I can't subtract that, right? That would actually be a negative number. So I don't want to do 1/9. What I want here is the 1/10 guy. For Webster purposes, I'm always going to write it in this order right here, so that it's always the smaller whole number less than the fraction, the improper fraction, less than the larger whole number. So when I flip everything, the smaller fraction is always going to be on the right-hand side, and that's the one I'm going to subtract. This actually ends up being the largest possible unit fraction that I can subtract. It is the way it is. And if I always stick with sticking it on the right-hand side, then I'll always pull the one on the right-hand side. Some people get to where they can see this process and they know what's going on, and so they'll put the 1/10 over here. I don't care as long as you know which one's the smaller one, because if you try to subtract the 1/9, you're going to get negative answers here, right? And that's what I want you to not do. Okay, so here's the idea. You have a 2/19. We're going to subtract or pull out the largest possible unit fraction, which we just said was 1/10. If I were you, I would make a point of boxing or circling or something what it is that's the unit fraction that I'm pulling out, because that will help you in a minute. Because remember, I don't want the subtraction, I want a sum of unit fractions, right? So my answer, my final answer, is going to look just like all these up here have looked. It's going to be a sum of unit fractions. So I need to somehow remind myself of this 1/10. I've seen a lot of people do the work right, but their final sum doesn't look right because they leave off one or more of these unit fractions. So just be aware of that. Okay, so now I'm looking at this, I'm like, oh, okay, 19 and 1/10, that's kind of a pain. I need a common denominator. It's an easy one, 190. For this first one, I just multiplied by 10, so that's a 20, and the second one I multiplied by 19, so that's a 19. And lo and behold, the leftover is 1/190th, right? Which is kind of a big denominator, but it's okay, we can work with it. So now I just need to go back and rewrite this as a sum, and we'll be okay. So 2/19 is equivalent to 1/10 plus 1/190th. That is my answer. Okay. So when I go back and I compare that to the Rhine Papyrus, 2 over 19, they have 1/12 plus 1/76 plus 1 over 114. That just reconfirms for us that even though we don't have the same answer as the Rhine Papyrus, it means that all of these are not unique solutions, right? Not all of these are unique solutions. So the Egyptians did things a little bit differently, and that's okay. The interesting thing for us, though, is if we're all doing Fibonacci's method, if on a test I say you must use Fibonacci's method, and we all pull out the largest possible unit fraction, we will all pull out 1/10. And if we do our arithmetic correctly, we will all have 1/90th left over, okay? And so then this is a unique solution, right? For Fibonacci, if I just keep on doing Fibonacci's method, we do get a unique solution. So there are other ways to do it, but if we all use the same method, Fibonacci, we all get the same thing. When we all used the 2 over n table before, that didn't always happen that way, right? And if you use the splitting identity and then, oh, I already moved that one. If you use the splitting identity and then you did something else different when you split this up, if you didn't split 5 into 2 and 3, if you did 1 and 4, like I mentioned at one point, then you're likely to get a different answer, right? Those are not necessarily unique. But for Fibonacci's method, they are. So we should all get the same answer on that, which is kind of interesting. But still yet not the same as the Rhine Papyrus, dang it. All right, so we don't quite know how they got all of their things, but sooner or later they seem to have come up with a similar table that everybody used, which is really interesting. All right, here we go, 6/7. I want you to work on it real quickly. Do it on your own. I want you to use Fibonacci's method. Work it out, see what you come up with, and I'm going to work it pretty quickly. You come back and tell me what you have, or check with me, make sure you've got the right thing. So go. All right. I happen to know that 1/2 is the largest unit fraction that'll come out of 6/7 because that's really close to the whole. And whenever I get a common denominator with these guys, 12/14 minus 7/14, I just have a 5/14 left over. So unfortunately for us, this is not a unit fraction. So I'm going to do it again. So with Fibonacci, you just keep on working off the remainder over and over again, and you just keep pulling the largest possible unit fraction. Well, I happen to know, and if you don't know, use that little technique, play with it, figure it out. I happen to know that 5/14, the largest unit fraction that I can subtract out of that is 1/3. If you want to play with the decimals and see what they are, go for it. But to me, it's just easier for me to play with the fraction off to the side and figure it out. That's going to be 40 seconds. 15 40-seconds minus 14 40-seconds. Check me, make sure my arithmetic is good. And that actually does give me 1 unit fraction, so 1 over 42. So hopefully play with it a little bit. Make sure you're getting the same thing we are. And when you're done, come back and write it as the sum of unit fractions, because that's the way the Egyptians did it. Yay! So I've got 6/7 is equal to 1/2 plus 1/3 plus 1 over 42. All right. So I think that is my 2 methods that are more modern. Those are not the methods that we're pretty sure those are not necessarily the methods that the Egyptians used. Let me see other notes that I've got going on here. So I already told you that there can be multiple representations, so we're good there. mostly done with unit fraction decomposition. I know that's really exciting to everybody. Yay! That we're pretty much done. If you're looking for some problems to work on other than the ones we just did, like if you want a little bit of fraction practice, go back and pull some of the ones that you did with the splitting identity, do them with Fibonacci, use some of these for splitting identity, but you might try 3/47. You might try 4/65. Some of these are not as nice as others, that's okay. And I've got 5/32. Okay, so try those. See how they work out for you. If you have any problems with them, like I said before, get with some partners, see me, let me know if you have issues, and we'll work them out. So that's most of that stuff for the Egyptians. There's some other stuff in Chapter 2, so you should be finished reading Chapter 2 this week, hopefully. Read everything that you haven't read yet. We're going to cover a little bit of stuff with the Plimpton 322 and some geometry that's in the rest of that chapter, but I'd like for you to go ahead and read it, and then we'll wrap that up next week, I think, or this week. We'll wrap it up this week and probably start moving on to the Greeks. That's the next civilization that we're going to look at, ancient Greeks. Yay. So if you have questions, let me know. Otherwise, good luck with everything, and I'll see you later in the week.